Andrew Kai, and I'll actually be doing problem 3 now. So let's just start reading over this problem. So Holstein hold up. So Farmer Rob wants to steal Farmer John's cows. So he wants to choose some cows to cow and nap. And although he's strong, there's a limit to how much weight he can carry. So there's again just like some weight limit that's going to be X in this problem. And he also and the thing is he must pick up all the cows at once. We can only steal cows located in contiguous stables. So like they all have to be in a row. We can't just choose like stable 1, 3, 5, 7, 9. So each cow's a milking value that determines how much money Rob will get from a single cow. So he wants to maximize some of these milking values. So what we're trying to find is just the maximum sum of the milking values again, and that's all we're going to return. So let's look at how the input-output is going to work. So let me just delete this code. Okay, so let's see how the input-output is going to work. So first of all, we have n, which is just the number of cow stables. Which is the number of cow stables. So n is just going to be like the total number of cows. Then second of all, we're going to look at second of all is just x, the maximum weight that he can lift. Then it's m of I, which is just the milking value of the ith cow, and then w of I, which is just the weight of the ith cow. So let's think about how to do this. So for example, let's look at the first sample input. So we have 3 stables. So there are going to be 3 different cows. So let's just write, here's a cow, here's another cow, and here's another cow. These are cows, guys. So this first cow will have milking value of 1. So this is m of I. Second cow will have milking value of 1. Third cow will have milking value of 1,000. First cow will have a weight of 2. Second cow will have weight of 1. Third cow will have weight of 2. So like 2, 1, and 2. So again, since we want a total weight to be less than or equal to 3, because again 3 is the maximum that Rob can lift. We cannot lift all 3 cows. So basically, what we do here is we can either lift these 2 cows or these 2 cows. And obviously here the optimal one is just the latter 2 cows, where the total milking value is 1,001. And that would be our answer. Now, what's an efficient way to do this? Because if you look over here, like initially you might just be able to think, well, why can't we just go over like every single contiguous combination of cows? Or maybe after that, you can think about doing something like, I don't know, like prefix sums, right? But if you notice, we have n, which is the number of cows, is less than or equal to 10 to the 6, and that's like 1,000,000 cows. So we can only do something to like n, maybe like n log n. But like O of n is a maximum. O of n or O of n log n. Let me just write this down. N log n. Like we can't do anything like O of n squared because then that's way too big. So how do we do something that's O of n? Well, let's think about an algorithm. So let's just think about like how to do it naively. So let's say we have a bunch of cows. Let me just draw a bunch of cows. Give me a second. So these are all cows, as you can see here. So we have their m of I and their w of I here. Then what we would do first is just like, let's say we take this cow, right? So we check that the mass is small enough so that we can actually lift it. Because let's say m of I is greater than x, which is the maximum weight that he can lift. Then of course you can't lift this. So let's say you can't lift it, and like you're like, cool, I can lift this cow. So yeah, you lift this cow, and then our current maximum milking value is just going to be this m of I. And then next of all, we can look at the next w of I, right? You can look like over here with this cow. See, can we lift this cow? Like, assuming we're already lifting this cow. If the answer is yes, then let's just add that, right? Let's just lift it. And then we just keep doing it. So let's say we can lift these 3 cows initially. And so the total, so like right now the running max will be m1 plus m2 plus m3. And obviously, since all the milking values are non-negative integers here, lifting a larger lifting a set of cows will always be better than lifting one of its subsets, because again, the more cows, the better. Like assuming that you lift all the previous cows. So what I'm saying is that, like, let's say we have a subset of cows and we can add one more cow to it while still being under the maximum weight restriction, then we should do it because that must at least weekly increase. So like make the new total greater or equal to the old total. Now what? So let's say we can lift these three, but we can't lift this fourth one. So then if we want to lift this fourth one, we'll have to drop one of those, like for example, the first one, right? Which means that that's what we're gonna have to do. So let's say we lift the fourth one. Then we're gonna have to check, can we lift, so we can't lift all four of these at once. Now let's check if we can lift these three at once. And let's say we can't, because that's still too heavy. Then we can check if we can lift these two at once. And let's say that is the case. So then we drop these two. And then our running weight would be M3 plus, I mean, our running maximum milk value would be the maximum of M1 plus M2 plus M3 and M3 plus M4. And then that's what we're going to keep on doing. We're going to see the we're going to look at the maximum amount of cows that you can, contiguous cows that you can lift, assuming that the last cow you lift is like a specific value, like for example at the ith position. And then we're just going to keep incrementing I over and over again. And then using that, we're going to like increment the starting cow position as well, based upon based upon like the maximum number of cows you can lift at once. So let's put this into practice. So first of all, I think it'll make more sense as I code it through. So first of all, let's make a buffered reader. We can't use scanner this time because, again, look at the constraints. And it's going to go to 10 to the 6. So there could be like 10 to the 6 input lines. And that's going to be too much. That's going to time input out. I mean, that's going to time like a scanner out. So what we do here is just we have a buffered reader. Input equals new buffer reader new input stream reader system.in. Boom, boom, boom. The next of all, we have a string tokenizer. st equals new string tokenizer. Input dot read line. This is just because the first line contains both n and x. So now let's see what to do next. So first of all, let's just create int n equals integer dot parse int st.next token. Then next of all, let's look at x. Look at this max bound. It's pretty big. So let's do long x equals long.parse long st.next token. Boom, boom, boom. Then let's input these next two lines, each with n numbers. So first would be milk equals new int, and then int weights equals new int n. So what we do here is we just, for example, let's just make, so this st would then represent like the next line by this. Then for int I equals 0, I less than n, I plus plus, we just enter like the milking values of each cow. So milk I would just be like integer.parse int st.next token. And the same thing for the next line. The next line just goes over all the weights of the cows. So st equals new string tokenizer input dot read line. Cool. For int I equals 0, I less than ni plus plus, we have weights I equals integer dot parse int st.next token. Yeah, so far we finished inputting all this input numbers, and now we can actually get to solving the problem. So first of all, let's do what we did in the initial step of our algorithm, which is just see how many cows we can initially lift up at once, assuming like we start at the 0th cow. So like let's say let's just have, so let's say, okay, so first of all, before we do that, we have to look at which cow we can actually pick up first, because there's going to be those weird cases with like W of 1 is greater than X, which means that you can't even pick up just the first cow by itself. I mean, W of 0 is greater than X, so you can't even pick up the first cow by itself. So you have to take those into account. So let's just create an int to represent the beginning position. So for example, if you could pick up the first cow, then beginning is just 0. But like, let's say the first 5 cows, like 0, 1, 2, 3, and 4, are all too heavy to pick up, even like just like individually. Then beginning would be 5, because you cannot pick up cows 1, 2, 3, 4. So while weights beginning is greater than let's see, so greater than X, then we have that beginning plus plus. However, we have if beginning is equal to N, then this means that we can't pick up any of the cows, which kind of sucks, because then the answer would just be 0. So it would just be 0 if we can't pick up any cow. Because again, we're looking at the maximum milking values of a set of contiguous cows. But if you can't even pick up a single cow in that, then its maximum sum is just 0. So then, we would just, in this case, we would just print out 0, and that's the end of it. So then let's do the actual meat of our algorithm now. So if beginning is not equal to N, then, so this is, all right, so for this, we have to look at, for like what we want to look at is like the beginning position of like our contiguous set of cows and the ending position of our contiguous set of cows. So for example, we have to look at, oh wait, I can change color, that's crazy. So for example, we can look at like, I don't know how to change color. This is the beginning position and this is the ending position. And we have to like keep them as variables, because those are the things we have to update. So let's say in point 1 would just be the beginning position. So initially that would just be, the only cow we have is the one at the position beg. So like the first cow that we can actually pick up. So then the beginning position and the ending position would both just be equal to this. Then we have let's see what other variables we have to store. So first of all, in our algorithm, of course, we have to store like the total, the total amount of milk we have, so that if it's greater than the maximum, we can just update the maximum. So let's just do long tote equals, right now it's just the milking amount of the beginning cow. That's the only cow in our current contiguous set. Then we have to have like the maximum milking value. So because again, that's what we're gonna print out. That's what we want to find. So we can have long max equals, currently it's just the total value, but we will be updating max as we go through algorithm. And then finally, we have to look at our current weight. So again, this is just because, again, like we have to look at our current weight, because like if our current weight exceeds X, which is like the total amount of weight that Rob can carry, then like then that tells us we have to kind of move on from the first cow, or from the first 2 cows, or so on and so forth. So let's just do long current weight equals weights beginning. All right, and our algorithm will just keep going until our second thing's at the very last cow. So what we do here is we just keep iterating, right? Like we just keep iterating over and over until like point 2, until point 2 is n-1, and then we're like, okay, we can't like try going to the next cow, so then we just end it. So while point 2, that's an n-1, let's see what we can do. Then so first of all, we have to see if so our 2 cases is if like adding the next, okay, so let's say we have like our current contiguous block is these 4, right? These initial 4. Then our 2 cases represent, basically we add the next one, if we can add the next one and keep the initial 4, or if we have to add the next one, but we can't keep the initial 4. So the first case means that current weight plus weights of this new point would be less than or equal to x, because again we can actually lift the current ones plus the new one. Then we will just increase 0.2 and we won't have to change 0.1 because again we just add this cow to our contiguous set. Then current weight would just again be added by weights 0.2 now, and it's not 0.2 plus 1 because we already increased 0.2 here. Then what else do we do here? We have to add to our total milk. So because again we add one more cow, so total is plus equals milk 0.2. Cool. Now let's see what else here. So also, by the way, we just do if toe is greater than max equals toe, because again this represents our max milk value. So if our total right now is greater than maximum, of course it has to be a new maximum. Now what else? So this is an if statement. There's going to be the other case where we can't incorporate like this one while incorporating all 4 of these initial cows. So what we do here is just, first of all, we take this current, what we do here is just we remove this first cow, and then we just go through the while loop again to see if we can incorporate this cow and these three cows now, and then so on and so forth. So basically what we do here is we have current weight, and then we just subtract, since we're just removing the first cow, we just subtract weights weights 0.1, then toe minus equals milk 0.1, and then 0.1 plus. And all this does is again completely remove the first cow. So yeah, I think we are basically done here. I think also this should be a small case that I could include here. Basically, this case is that, let's say like you're just iterating through, you're just having fun, you're just iterating through your algorithm. Let's say boom, boom, boom. But then you come across, like, you stumble across this cow, which is like really fat. So basically, he's like his weight is larger than X. So it's kind of like our initial thing, but like somewhere in the middle. So that obviously means that like we can't do anything. So what we do here is that if weights 0.2 plus 1 is greater than X, because again, actually what we do here is if anything, okay, let's see. So what we do here is, let's say like this weight is greater than X, right? So then obviously like you won't ever go through this, and eventually you'll have like nothing over here, right? Like because since if you can't do this if, you'll have to go through the else loop. So eventually your set won't have anything, right? And then it would go through this even if 0.1 and 0.2 are equal, which is kind of whack. So because we don't want that. So basically what we would do is if, like in this case, 0.1 would actually be greater than 0.2, because like 0.1 would be like over here and 0.2 would be over here, to represent that like there's like 0 cows in there. Because if 0.1 and 0.2 are equal, then that represents 1 cow. So what we do is if 0.1 is greater than 0.2 here, then all we have to do is then we just increase 0.1 and increase 0.2 by 1. What that does is that basically just completely skips this cow. So then we can try looking at so then we have 0 cows, and we can start by looking at the next cow after the one that's greater than X. Now, let's see. I think that's the entire algorithm, so let's just print out our answer. Print ln max. Let's see if there's any issue here. Run code. Okay, for test case 0 it works. There might be some weird test cases though, because there's like definitely a lot of pathological solutions to this. So let's see. Oh, and it's accepted. Nice. So yeah, that's basically the solution. If you have any questions, comments, concerns, whatnot, feel free to speak up right now. Otherwise,